Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the Einstein's explanations for photoelectric effect. We have already discussed in the previous video that Albert Einstein was awarded with Nobel Prize for explanation of photoelectric effect with the help of quantum theory of light, and the conclusions which Einstein gave are now known as laws of photoelectric effect. First law is the fact that for each metal there is a certain minimum frequency of radiation that is called as threshold frequency, below which photoelectric effect does not take place no matter how high is the intensity of radiation, and the value of threshold frequency depends on the metal on which radiation is incident. So according to Albert Einstein, he stated, as you all know, that light is made up of photons, and according to him, when photon strikes any metal surface, then one photon strikes with one surface electron only, and that one photon transfers its complete energy to that one surface electron, and that one surface electron comes out from the metal surface by utilizing that energy into two parts. The first part is being the work function, and the second part is being the kinetic energy of the electron. So obviously we know that the minimum energy that is required to eject the electron is h nu naught, and that is equal to the work function. So this is called as the threshold frequency. So this threshold frequency is the minimum required frequency for the photoelectric emission. But intensity is independent of this emission is independent of the intensity of light, which was one of the failures of that wave theory of classical physics to explain the photoelectric effect. And the next, he said that the process of photoelectric emission is an instantaneous process, and there is no time lag between the incidence of the photon and the emission of the electrons. See, as he already stated that the photoelectric emission takes place by the collision of one photon with one electron, and this photon transfers its complete energy to that single electron only. Okay, now this is the collision is an instantaneous process, we know, and according to Einstein, the collision was between a photon and electron, and instantaneously photon transfers its all energy to that single electron, and that electron is ejected out from the metal surface with no time delay. And this was obviously the practical observation which was observed in the photoelectric effect, that there was no time lag between the two events. The event 1 is the incidence of the photons, and event 2 is the emission of the electrons. So there was no time delay between these two events, and Einstein explained that there should be no time delay as well, because this is occurring due to the collision of photon and a single electron, and collision is an instantaneous process. Now the third one is the fact that photon strikes only one electron, as we have already discussed, and no matter how large is the energy of the striking photon, it will transfer all of its energy to only one electron, and that single electron will utilize that energy partially to compensate the work function of the metal, and the remaining energy becomes the kinetic energy of the electron. Now the fourth point is the fact that number of photoelectrons emitted per second, which is the photocurrent, is directly proportional to the intensity of radiation and is independent of the frequency of radiation used. So in this case, in the fourth law, he stated that the number of photoelectrons emitting from the metal surface per second is dependent on the number of photons which are striking the metal surface per second. And we know that the number of photons striking the metal surface per second per unit area are also called as photon flux. So actually, according to Albert Einstein, the photocurrent was directly proportional to the photon flux. Okay, and the velocity of emitted electrons vary between 0 and a definite maximum. See, initially it was observed that by striking the different photons of same energy, it was observed that the electrons which were emitted from a single metal were having different kinetic energies, which means that each similar photon was emitting an electron which was moving with different speeds and different kinetic energies. And this was due to the fact that in the emission of electrons there is some loss of energy in any form, in any you can say that in a sound, a small popping sound, or any spark which is produced during the emission. So there was some energy loss with the electrons when they are emitted, and obviously therefore the energy loss was not same for all the electrons, and hence the kinetic energy of all the electrons was different. But there were some electrons which were having the maximum kinetic energy, and those electrons were not having any kind of loss, and the complete energy received by those electrons minus the work function was converted into their kinetic energy. So those were moving with the maximum kinetic energy. And it was observed that the maximum kinetic energy of the emitted electrons were independent of the intensity of the radiation and was linearly dependent on the frequency of the radiation. Now let us discuss that what is intensity. Now intensity is energy per unit area and per unit time. Okay, or you can say that power per unit area is intensity. Now we know that energy of one photon is h nu, and let us suppose that n number of photons are striking the surface, and this is a into t. Now we know that n divided by at is the photon flux, and this is h nu. So we can say that the intensity of the radiation is phi into h nu. Now you should listen very carefully that when let us suppose that we are incidenting ultraviolet radiation on a metal surface, and we wish to increase the intensity of the same radiation. Now as the radiation is still ultraviolet, so we are not changing its frequency. So we are not changing the amount of energy carried by single photon. But what we are changing the photon flux, or we are increasing the photon flux to increase the intensity of the radiation. Okay, so in the complete photoelectric effect, if we will say that we are increasing the intensity of the given radiation, then obviously we are not changing the energy of a single photon, but we are changing the amount of photon flux. So obviously the electrons which were ejected with some energy was depending on the energy of a single photon. And as you know that the energy of single photon is not altered by increasing the intensity, hence we can say that the maximum kinetic energy or the kinetic energy of the electrons was independent of the frequency, it was independent of the intensity of the given radiation, and it was linearly depending on the frequency of the incident radiations. Okay, now photoelectric effect is the result of collision of two particles. One is photon of the incident light, and the other one is electron, which is on the surface of the metal, which is illuminated with the radiations. So we have already discussed this fact that photoelectric effect is result of this collision between photon and electron. Now the eighth point was that all the energy of a single photon is being transferred only to a single electron, which is partially utilized as work function and kinetic energy of the surface electron. I think we have already discussed this point. And the ninth point is the fact that when electrons are emitted from the metal surface, then some part of the energy received by the electrons is also lost in form of the heat. Hence the emitted electrons have different kinetic energies, and some of the emitted electrons are absolutely having no loss of energy, and hence their kinetic energy is maximum. This point is also being discussed by us. Now this is the experimental setup in which photoelectric effect was conducted, and in this setup there is a evacuated tube. Evacuated means that vacuum was set up in the tube, and this is a cathode and this is a anode. So the light of sufficient energy, which is having an energy of h nu greater than work function, is incident on this cathode, and as soon as electrons are emitted from this cathode, current was registered on this emitter. So there was a observation. Now first of all, let us discuss this equation. So initially Albert Einstein gave this equation: h nu is equal to h work function plus kinetic energy. So this was being challenged as for some of the electrons, the sum of work function and kinetic energy was not equal to h nu. In fact, this sum was less than h nu. So this equation was challenged, and then Albert Einstein changed the equation, and there was a slight change that he wrote Ke max, and he stated that this equation is valid for only those electrons which are having the maximum kinetic energy. So obviously there were some electrons which were having no energy loss in the emission, and hence their kinetic energy was maximum. So according to Albert Einstein, this equation is only valid for those electrons which does not had any loss of energy while emission. So the work function is also equal to h nu naught, where nu naught is the threshold frequency, and h nu is equal to h nu naught plus half mv square max. And later on, what you can see that Albert Einstein used the photosensitive metal as cathode, because as soon as the electrons were emitted out from this cathode terminal, they were repelled by the cathode and they were attracted by anode, or we can say that they were accelerated between cathode and anode towards anode, and the current was being registered in the emitter. But it was also observed that if there was no potential difference between these two terminals, some current was still observed in the emitter, which means that if we short circuit these two terminals like that, then also some of the electrons were moving from cathode to anode on their own. And this was due to the fact that the electrons which was emitted from in this effect were having some kinetic energy, and by that kinetic energy they were moving from this terminal to this terminal. So in the presence of no potential difference, some current was also registered in the emitter. Now Albert Einstein just inverted the voltage. It means that he connected the positive terminal of the battery with this photosensitive metal and made this terminal as anode and the other terminal as cathode. So he inverted the voltage, and he increased the voltage in the negative direction. So he observed that the current which was initially flowing when there was no voltage was becoming zero at a specific value of voltage. So obviously we have already discussed that when electrons were moving from this terminal to this terminal without any accelerating voltage, they were moving due to their kinetic energy, and obviously that kinetic energy, if that kinetic energy is equal to EV naught, where V naught is the negative potential at which saturation current becomes zero. So we have discussed that on inverting the terminals of the apparatus, Albert Einstein created a negative potential on the electrons, and electrons were retarded due to that potential. And if at a certain potential, if the electron of highest kinetic energy was being stopped, then all of the other electrons were automatically getting stopped, and the current in the emitter was becoming zero. So this is called as stopping potential, which is the negative potential at which the photocurrent becomes zero. and obviously this stopping potential will be equal to half mv square max. Okay, so this mv square max, half mv square max, is being replaced by this ev naught, where v naught is the stopping potential. So this is the final equation of photoelectric effect. Now Albert Einstein plotted a graph between saturation photocurrent and intensity of the given radiation. As we have already discussed, the intensity of the given radiation is the photon flux, obviously, because we can not change the frequency. So this is the photon flux, and the photon flux is the number of photons incident on the surface per unit area per unit time. So if we are increasing the number of photons incident on a surface per unit area per unit time, then obviously the number of electrons emitted from that surface per unit area per unit time will increase, and the number of electrons emitted per unit time into the charge of any one electron is the saturation photocurrent. So there was a linear relationship between this saturation photocurrent and the intensity of that given radiation. So this was the first observation of the graphical observation of the photoelectric effect. And now Albert Einstein plotted the graph between photocurrent and accelerating voltage. Now, as we have already discussed, this photocurrent was becoming zero at a negative voltage, which is called as stopping potential. So we are not writing negative here because stopping potential is itself a negative potential. So this is the stopping potential, and on increasing the accelerating voltage, the current was increasing, and obviously when the voltage was becoming zero, this is negative voltage, and we are increasing this negative voltage towards zero. Okay, so we are decreasing the magnitude of voltage, and if we are considering the negative sign also, then we can say that we are increasing the voltage. And when voltage becomes zero, then also some current was observed. This is due to the fact that some of the electrons were reaching the anode on their own due to their kinetic energy. And on further increasing the accelerating voltage in the positive direction, the electrons were accelerated towards anode, and a time will come when, let's say, per unit time 100 photons are being 100 electrons are being incident, 100 electrons are being emitted from the metal, and those 100 electrons will not reach the anode with simultaneously. In fact, the fastest electron, which is moving with the highest kinetic energy, will reach the anode first, and then the slower electrons will start to reach, and therefore the photocurrent will increase. But as soon as per second all the 100 electrons will reach the anode, the current will attain the saturation value, because continuously 100 electrons are being emitted from the metal surface per second, and continuously those 100 electrons are reaching the anode. So current will attain a saturation value, and now if we wish to increase the current, we increase the intensity of the same radiation, which means that we are increasing the photon flux. So if we are not changing the frequency because we are using the same radiation, then again stopping potential will remain same, but this saturation current will be increased, because let's say the initial photon flux was 100 photons per unit area per unit time, and we are increasing that photon flux to 200. So it means that 200 electrons will be emitted per second, and therefore saturation current will be doubled. And in the same way, if we further increase the photon flux or intensity, then again saturation current will increase. Okay, now in the second observation, if we have increased the frequency of the radiation, but we have kept the photon flux same, which means that, let's say, we are initially using infrared radiation, then we are using violet radiation, and then we are using ultraviolet. So we are continuously increasing the frequency of the radiation, and therefore the magnitude of stopping potential will increase. And let me remind you that in this equation, this is the magnitude of stopping potential. This is magnitude of stopping potential. So we do not have to keep the negative sign here. Okay, so this is the magnitude of stopping potential. So it was observed that on increasing the frequency of the radiation, the magnitude of stopping potential was increasing. But if we are keeping the photon flux same for all the three radiations, which means that we are keeping the number of photons incident per unit area per unit time on the metal surface of all the three radiations same, then obviously the number of electrons emitted by all the three radiations per second per unit area will remain same, and hence the photocurrent, saturation photocurrent, will saturate at a same value, constant value. So these three graphs will meet at this constant value. Okay, now there was a simple graph which was plotted between stopping potential and frequency of radiation, and we can find out the value of stopping potential in terms of nu, like that. And you can see that this is y, and this is m, and this is x, and this is c. So this is y is equal to mx minus c. Now c is this complete value, h nu by e. So you can see that the slope of this graph is h by e, and if we draw two graphs for different metals, then you can see that for if the work function of metal is different, then their threshold frequency will also be different, but their angle or we can say their slope will be same, because slope is h by e. So these will be the graph between these two quantities, stopping potential and incident photon frequency. And these graphs will not be plotted in negative direction, because obviously stopping potential is already negative, and if we are taking this graph to in the negative direction, we are making the stopping potential positive. And if that potential is positive, then it would not be the stopping potential, and it would be accelerating potential. So we will not take these graphs to the negative, we will take the dotted lines only. So now this was a complete explanation of Einstein for the photoelectric effect, and I think now you would not have any query or any conceptual doubt in this photoelectric effect chapter. And in the next video I'll be bringing level 1, and in the next video will be the level 2 problems of photoelectric effect. Thank you.